Hello, welcome you all in the chemistry of carbonyl compounds. In my previous lecture, I gave you the reaction mechanism for Beckmann rearrangement reaction. Now here I will tell you one more reaction which is similar to Beckmann rearrangement, that is Baeyer-Villiger oxidation reaction. For Baeyer-Villiger this rearrangement reaction, so this reaction, some features of this reaction here, if we have any ketone, then this after oxidation that will be converted to esters. So usually what we have seen, if we have any alcohol, it can be oxidized in presence of a strong oxidizing agent like either KMnO4, K2Cr2O7, and that further it would be converted into acid. But here if we have this ketone, then ketone can be converted into ester. And the oxidizing agent that we will use, per acids are the oxidizing agent. These are the per acids are used as an oxidizing agent. Like if we may have hydrogen peroxide, or we may have other per acids like we have per acetic acid, we may have per acetic acid, or we may have per benzoic acid. If we have in place of this methyl, we have this phenyl group. So we have per benzoic acid or metachloro per benzoic acid, CPBA. Metachloro per benzoic acid means if we have this per benzoic acid, this is per benzoic acid similar to here. If this is our per benzoic acid, then at this meta position we have the chlorine. So this is metachloro per benzoic acid that can also be used. So in presence of these per acids, the ketone can be converted into ester. So suppose if we see the example, then if we have this ketone and in presence of per acid, and suppose if we have this one and we have any per acid, suppose if I write this, suppose directly I write per acid only, per acid, any per acid may be there, then this would be converted into ester. So between this carbonyl compound, it is similar, what I told you, this is similar to the Beckmann rearrangement. In Beckmann rearrangement, what you saw, amide was formed. Okay, from a ketone, amide was formed, and between one of this carbonyl compound and this methyl carbon, the NH group, I inserted the NH group. But here between this carbonyl compound and this methyl group, I will insert one of the oxygen atom. In place of NH, I am inserting one oxygen atom, and this is being converted to ester. This is now ester. Okay, so this is the symmetrical type of molecule. Now, if this molecule is unsymmetrical, suppose here different groups, these two groups are different, then we have to select where this oxygen should insert, either here or here. Means in that rearrangement will take place, one of this will migrate, either this migrate, like this migrate, similar to that of Beckmann rearrangement, and we should see which group should migrate. So like here, the migratory aptitude, what migratory aptitude should be followed? Migratory aptitude, what we should follow? It is a little different to the Beckmann rearrangement. So first here, phenyl migrate. If we have two phenyl and hydrogen atom out of these two, we should select this one. This will migrate. Then it follows the same order like that of Beckmann rearrangement: tertiary, secondary, and then primary. And next thing here, stereochemistry. If any stereochemistry is given, then stereochemistry remains same in the product. Stereochemistry remains same in the product. Okay. Now I should give the mechanism for this. Now if we have simple symmetrical type of ketone, first in presence of H plus, so we have a per acid. Suppose if per acid any, this is our per acid, and this will ionize the, after this it will give you the minus, so this will can break and this can give you the minus charge over here and it will become plus. Now this H plus, it will help in this protonation of this oxygen atom, and after this protonation, a positive charge is coming over here, and now this carbonyl carbon has become strongly electrophilic. Now we have this will act as a nucleophile. Per acetate ion, this is our per acetate ion, this will act as a nucleophile and it can attack over this electrophilic center. Positive charge will get neutralized, and what you can write OH over here, and this oxygen, this carbon is attached to this oxygen, and now another oxygen, and now this carbonyl one and this one will form. Okay, so in another step you can see the rearrangement. Okay, so how? First, here the double bond that would be restored, valency of carbon would be increased, and now either this can break or this will break. Okay, so suppose, because this is a symmetrical type of molecule, otherwise we should select any one. By the migratory aptitude order we can select one. So suppose I migrate this one and this will migrate to here, and this oxygen-oxygen bond being the polar bond, it will break. So one of the driving force for this rearrangement is the formation of acetate ion being the resonance stabilized ion, so that would be formed. So how we can write? So now this one of the this double bond, it is converted into double bond, and a bond is now formed between this carbon and this oxygen. This oxygen forms a bond with this alkyl group, and suppose this is one of the alkyl, and plus we have acetate ion. Now in next step, this would be converted into ester, and plus we have acetic acid. So this would be the product. So this is the simple mechanism. Only step that we should follow here, the rearrangement reaction. And driving force for this rearrangement reaction is the formation of this acetate group, which is a resonance stabilized one. Now if we have a example where we have two different groups, suppose if we have phenyl group and another is the methyl group, and if we do the oxidation of this ketone, then what will be the form? Only thing that we have to do, we should follow the migratory aptitude. So here, which group out of these two group, no doubt what I have told you, this phenyl group migrates, and phenyl group migrates, and what I should do in between this carbonyl carbon and phenyl, what I should write? I should write the oxygen, and that should be converted into one of the ester. So now I have converted this into ester. Simply I have written the oxygen in between this carbonyl carbon and phenyl. So this comes, the final product is, we can obtain this final product after the migration of phenyl group. So if we have suppose phenyl group over here, so one of the phenyl group over here, and we have CH3 group over here. This same mechanism would be followed, and phenyl group migrates and we will get this product, that is the ester. Now next example is, suppose in place of here if we have a cyclic ketone, then how can we write the product? Suppose if we have a cyclic ketone, and then here the product, this would be now converted into 7-membered ring. In my previous lecture of Beckmann rearrangement, the ketone, the cyclic ketone that would be converted into, that was converted into the caprolactam, which was 7-membered ring. Now here it is again, it is converted into 7-membered ring, and one of the oxygen, what we have to insert one oxygen between this carbonyl carbon and either this carbon or this carbon. Only thing is we have to insert this oxygen between this carbonyl carbon and this one. So let's insert here and now convert this one into a 7-membered ring. So this is a 7-membered ring and this is called as a lactone, or this is a cyclic ester. Lactone is formed. So how we can write the mechanism for this? No doubt this oxygen is coming from this per acid. Suppose I write here H2O2 is the oxidizing agent. In presence of oxidizing agent, this would be formed. Okay, so first protonation. So this oxygen, this hydrogen, it may come from this per acid. This H plus may comes from the per acid, and if I protonate it, we have a positive charge over here, and in my next step I have suppose per acid. Suppose if we have now it will attack over here. Okay, so after that okay, now gain. So now either this can migrate. So if double bond is restored over here, if double bond is restored and valency of carbon is increased, we can break either this carbon-carbon bond or this carbon-carbon bond. So suppose, okay, so and one of this bond will break and this carbon like this. Okay. So what I may write? I may write OH, positive charge over here, and we have oxygen. This one is okay. Now this carbon is attached to this oxygen, and now this oxygen is now attached to this carbon. So the 7-membered ring is formed, and in my next step plus this OH minus, and in my next step lactone is formed. Okay, so this is the mechanism for this cyclic ketone. Now if we take another example, suppose what I told you in Baeyer-Villiger oxidation reaction, the stereochemistry remains same. Stereochemistry remains same. If we have one of the example, suppose we have now if this is the ketone, and suppose if we have a benzoic acid, then what should be the product? How can we write the product in this case? So what I told you now, so we have at one side we have this alkyl group, we have a methyl group, and at other side this is primary methyl group, and at other side we have this tertiary. So out of this tertiary and this primary, which should migrate? Tertiary will migrate. It means in final product I should insert this oxygen atom between this carbonyl carbon and this tertiary carbon. So the product that I can write, this should be the product that I may write. And here the stereochemistry that remains same. Stereochemistry in the product remains same. In the same way, if we have another example, now, so what should be the product? How can we write the product over here? So here, if you will see the neighbor of this carbonyl carbon, we have, this is the tertiary carbon and this is the secondary carbon. So according to the migratory aptitude order, the tertiary carbon that should migrate, and the group which migrates, then how we can write the product? In the group which migrates in between this carbonyl carbon and the carbon which migrates, we should insert a oxygen atom, and then we can get the product easily. So just we have to insert one of the oxygen atom over here and convert this one into a 7-membered ring like this. So now one of the methyl group over here and another methyl group. So what I have done, and finally the stereochemistry of this groups remains same in the product. So these are some of the examples of Baeyer-Villiger oxidation. Hope you are understood. Thank you.